Okay, this continues the lectures on friction. Now specifically, we take a look at kinetic friction. Okay, we begin by taking a look at what are called the empirical properties of kinetic friction. Okay, now once again, the word empirical in the scientific lingo means it comes from measurements and or data, observations that is based upon the observations of moving objects around us. We've discovered that kinetic friction obeys a couple of very simple properties. Some of these properties are intuitive, some of them perhaps not. Okay, first of all, the force of kinetic friction acting upon an object always opposes the motion of the object, not necessarily the acceleration. I'll demonstrate that in just a moment, that it opposes the motion. The force of kinetic friction always opposes the motion. Okay, and then as I said, not necessarily the acceleration. Let me clarify. All right, so for example, with my eraser sliding down a shallow inclined plane like so, as the eraser was moving down the slope, the force of kinetic friction was acting upon the eraser up the slope, that is, opposing the motion. However, because the eraser was slowing down, the acceleration vector was also pointing up the slope. So then therefore the force of kinetic friction always opposes the motion, but not necessarily the acceleration. Okay, that's fairly obvious if you think about it. Okay, and then secondly, this is somewhat counterintuitive, but the force of kinetic friction between two surfaces is actually independent of the surface area of contact. So for example, as the eraser here, say, slides down the incline like so, the force of kinetic friction acting upon the eraser mathematically actually has nothing to do with the surface area of the eraser itself in contact with the board below. The rate of heat loss does depend upon the surface area, but the value of the force itself does not. Okay, and then third, the force of kinetic friction is independent of the relative speed between the two surfaces. So for example, as the eraser slows down like so in this situation, the force of kinetic friction acting upon the eraser while it's slowing down doesn't change. It's essentially a constant. So independent of the relative speed between the two surfaces. So it's specifically with these two empirical properties here of kinetic friction, this then actually makes it easy to describe mathematically. So imagine how difficult kinetic friction, for example, would be to describe if the value of that force was changing as the eraser, say, slows down like so, or if it depended upon the surface area of contact between the two objects themselves. That would be mathematically difficult to describe. Turns out, however, that the force of kinetic friction is independent of the surface area of contact and is independent of the relative speed between the two surfaces. It's with the fourth and last property of kinetic friction that we now begin to quantify it mathematically. This is intuitive. Let me describe it first, and then I'll also demonstrate it. Okay, so fourth, the force of kinetic friction, I'm going to rewrite that phrase here for emphasis. Okay, the force of kinetic friction is directly proportional to the normal force So let me briefly demonstrate that to you. I'm not going to do so using my eraser and my board. Instead, what I'm going to do is I'm going to get a textbook. So just a moment, please. All right, so here's one of the physics textbooks. Okay, and now, right now, when the book is just sitting here on the table, the normal force acting upwards on the textbook is exactly equal to the book's weight downwards, mg, like so. The normal force in this case is a relatively small value, it's just equal to the book's weight. So then therefore, because the normal force is small, when I do this, the force of kinetic friction acting upon the white book that opposes its motion is a relatively small value as well. Okay, next what I'm going to do, however, is I'm going to take the textbook and I'm going to press it into the desk like so. So now when I do this, is the normal force acting on the textbook still just equal to the book's weight? No, it's equal to the book's weight plus the amount of force that I'm applying to the book downwards like so. Basically what I'm doing is I'm taking the two surfaces, the textbook, for example, and the desk, and I'm mushing them together like so. So then therefore, if I increase the normal force that's acting on the textbook by pushing down on it like this then actually makes it very difficult for me to push the textbook across the desk like so. The amount of friction that is acting on the book while I was doing that has gone up dramatically from what it was before when I was not pushing on the textbook itself. What this ultimately means is that the force of kinetic friction acting on the textbook directly is proportional to the normal force that's acting on it as well. Okay, once again, all of this is based upon empirical observations. Here's then how we write this last property here of kinetic friction mathematically. The force of kinetic friction is referred to as F sub k, and it's directly proportional to the normal force N. So if you increase the normal force, as I did in this simple demonstration, you then increase the force of kinetic friction. Now this right here is the proportionality symbol. When you have two quantities that are proportional to each other, this then means that there is a number that is present, a coefficient that is present that turns this into an equal sign. Here's how we write this coefficient. Okay, the coefficient is written as the Greek letter mu, and then we have a subscript k symbol here. This is referred to as mu sub k. Mu sub k is called the coefficient of kinetic friction. Now the coefficient of kinetic friction is an empirical property of the two surfaces. So for example, if I just use my eraser again, the coefficient of kinetic friction is not a property of the eraser. It's not a property of the desk. Instead, it's a property of the interaction that occurs between the eraser itself and the desk itself. In other words, it's at a fundamental level a description of how electromagnetically the atoms that make up the surface here of the eraser are interacting with the atoms that make up the surface of the desk when I do this like so. That's ultimately where the coefficient of kinetic friction comes from. Can we derive the coefficient of kinetic friction by examining the fundamental physics that occurs between the atoms that make up the eraser and the atoms that make up the desk? No, and the reason for that is because computationally, once again, there are just simply too many variables. Trying to derive the coefficient of kinetic friction between any two surfaces is impossible because of all the variables involved. It's like trying to predict weather, once again, more than 2 weeks in advance. However, measuring the coefficient of kinetic friction is easy to do, and I will actually have you do that in a mini lab exercise at a later date. However, before we actually get to that exercise and before we get to those details, once again, the coefficient of kinetic friction is an empirical property of the two surfaces themselves. So it's something that's measured. So it's an empirical property of the two surfaces. Okay, the number itself. The number itself, first of all, is dimensionless. It has no units. And the reason for that is because just look at the expression. Right here is a force in newtons. Right here is a force in newtons. So then therefore, this is newtons and this is newtons. This doesn't have anything. In other words, it has no units associated with it. It's a dimensionless quantity. Dimensionless, if I could spell the word. Quantity. Okay, usually in most simple situations involving common materials, usually the coefficient of kinetic friction is a small number. It's usually less than 1. There are some instances where it's actually greater than 1, like for example by, say, the contact that occurs between soft rubber and cement. In some cases, like with automobile racing tires and so on, those really big, fat, soft rubber tires, in some cases, the coefficient of kinetic friction that occurs between the two surfaces is greater than 2. This is ultimately, by the way, why we use rubber for tires, because when rubber interacts with cement, there is a rather large coefficient of kinetic friction associated with those surfaces, and then therefore, of course, it makes it safe for a vehicle to drive if you're basically having the vehicle sit on soft rubber. So that's why we use rubber for tires and so on and so forth, is because of the coefficient of kinetic friction itself being a large value in that instance. Okay, now let me go ahead and take you through a basic example here where if we wanted to, we can use an example like this to measure the coefficient of kinetic friction between two surfaces. Let's go ahead and access the problem associated with this lecture. I'm going to give you a moment here to copy it down as I read it to you. Okay, so a hockey puck with a mass of 100 grams has an initial speed of 5 meters per second while sliding across horizontal ice. We've seen this problem before. We saw this at the beginning of the unit on dynamics. We saw it at the beginning of chapter 4. Okay, the puck comes to rest after moving 10 meters. What we're now going to do is go one step further than the example that we did at the beginning of chapter 4. We're going to use this empirical data, if you will, that's given in this problem to calculate the coefficient of kinetic friction, U sub k. Okay, let me go ahead and do some erasing here. Okay, so let's go ahead and get to our problem here. First of all, let's note that the mass is equal to 100 grams. That's 0.1 kilograms. There are 1,000 grams in the kilogram, so let's convert to metric SI units. Okay, and then let's look at the kinematics once again, like we did in the earlier version of this example. So the puck is initially moving to the right-hand side at 5 meters per second. Let's say it starts at the origin. It slides to rest over here with a final speed of 0. Right here is the displacement x that's given to us as 10 meters. And then what we're going to do, like in the earlier version of this example, is we're going to use the third kinematics equation to calculate the acceleration. We'll find that the acceleration vector points to the left-hand side. Okay, now here's the third kinematics equation, like so, as we saw it for horizontal situations back in chapter 2. Let's immediately go ahead and plug in our zeros here. So we start at the origin and the object ends up at rest, like so. And then we run through the algebra here and solve for the acceleration A. And when you do, you arrive at this expression here, like so. And now we just plug in the numbers. So we're going to have here negative, and that then means, once again, that the acceleration vector points to the left. 5 squared and then divided by 2 times 10. This ends up being negative 1.25. meters per second squared, just like it was in the earlier version of this example. Okay, the acceleration vector then points to the left-hand side like so. Okay, and now we look at the dynamics here of the situation, just as we did in the earlier version of this problem. So as the eraser, wherever it is, as the eraser, after I let go of it, slides across the desk like so, we have then 3 forces acting on it. We have, first of all, vertically, the normal force and the weight mg. There's no acceleration vertically. These 2 forces cancel out. Now, earlier in this unit on dynamics, I was writing down these expressions for the normal force, for example, in problems as I went, but those expressions for the normal force never entered into the examples. Now they do, and the reason for that is because the force of kinetic friction acting upon an object is directly proportional to the normal force. So we need to know what the normal force is. You'll see that here as we continue in the problem. And then, as the eraser, for example, moves to the right-hand side after I let go of it, opposing its motion is the force of kinetic friction, like so, acting to the left-hand side, and it's, of course, the force of kinetic friction that gives us the acceleration A. So when I add up the forces here horizontally, we just have the force of kinetic friction is equal to the net force MA. This right here is basically as far as we went in the earlier version of the problem. But now what we're going to do is write the force of kinetic friction in terms of this empirical property. The force of kinetic friction is equal to the coefficient of kinetic friction multiplied by the normal force. Here's where we need to know what the normal force is. The normal force is equal to the eraser or the hockey puck's weight. So let's go ahead and plug that into here. Like so, and then notice that the mass cancels out. so. This then means ultimately that the coefficient of kinetic friction between the eraser and a desk has nothing to do with the weight of the eraser itself. Once again, the coefficient of kinetic friction is basically an empirical property that's describing electromagnetically how these atoms here are interacting with these atoms here. That has nothing to do with the eraser's weight itself. It's basically a description of the fundamental physics that's occurring here. Okay, now let's just go ahead and finish the problem. We're going to divide the G here to the other side, like so. And so then therefore the coefficient of kinetic friction is equal to 1.25 meters per second squared divided by 9.8 meters per second squared. Notice that all the units are going to cancel out. Let me go ahead and calculate out this value. So 1.25 divided by 9.8, and this comes out to be about 0.13. Like so. We usually measure out or write the coefficient of kinetic friction out to 2 decimal spaces in typical examples such as this. So this example here provides for us, if we wanted to, a means of finding the coefficient of kinetic friction. All that we have to do is let go of the eraser with some known initial speed, say 5 meters per second, and then measure how far it moves in coming to rest, 10 meters in this example. Ultimately then use that data to find the acceleration, and then the acceleration divided by g is equal to the coefficient of kinetic friction. Okay, I'm going to conclude this portion of the lecture here with the conclusion of this problem.